All right, let's go ahead and get started. So I have your homework up at the front and also this week's lab And so I apologize, I haven't finished grading your midterms. I'm like super duper close. And I was hoping to finish during lunch, but I've had something else come up with a pressing deadline. But I'm hoping tonight I will get through them. I again apologize. So I did want to talk to you just about a random announcement. Did you guys see the Grand Canyon University booth setup? He was there like last Thursday. And the only reason why I'm mentioning this, so, right, I have no interest in you going to Grand Canyon University personally, but the guy, I chatted with him and he was talking about that they're trying to get people interested in their campus. So if you would like to leave, you know, Southern Oregon, that might be an option. Or they were advertising just like free trips anyways. So even if you're not going to go, maybe you just want a free trip to Arizona. So if you're interested, maybe chat with me, because he was also talking about like we could get a whole group trip going or something. So that might be fun. And again, what I really want to put on your radar is not going to Grand Canyon University, but just making sure you're thinking of your future, right? And like, where are you going to go? And I know this is like an odd class because I have some like high school students and some college students, but you just want to be thinking about like, where are you going after this? Are you going to transfer? You know, what university are you going to? Do you want to leave Oregon? Like, there's a lot of things to think about, and it's never too early. And I'm more than happy to chat with people, you know, personally, so we can talk about all that. But, you know, just always be thinking about your next step. And then with that, right, search for internships. And if you want help with this, you know, just shoot me an email. Some internships or other scholarship opportunities. Right, so put all this on your radar, especially as you approach kind of winter break coming up now. That is a good time to try to figure out what you're going to do over the summer and try to apply for stuff. And again, if you want more help and guidance, I'm more than happy to help, but definitely think about your future and your next steps from here. All right, so now let's talk about the chapter. And so we've kind of gotten a little ahead of, or the lab has gotten ahead of lecture. So now we'll kind of go back and recap what you guys have done in lab. And so let's look at kind of the distinction between a physical change and a chemical change. And so kind of put yourself in the mindset, start thinking about last week's lab with the chemical reactions, kind of what happened. And so let's talk about physical changes though first. And so physical changes, this is something that alters the state or appearance, but again, not the composition. So can anybody think of some examples of physical changes? Freezing, melting, so those are good ones. Other physical changes. Yeah, so we could do, so mixing, that would be a good one. So I like that, food coloring. So right, we didn't change anything, and then you could separate them out. So that's kind of a key distinction, right, between like mixing. So yes, it could be difficult, right, to get out that food coloring, but you could still distill it or do something to try to separate those two back out. And so kind of with mixing, I'll put dissolving as well. So that's one that tends to trick people. So putting like salt into water. And so again, right, that doesn't change anything physically, just kind of dissolves it, and then you could redistill it back out, and you still just have salt and water. Anything else on the brain for physical changes? Yeah, I can't think of anything else. I mean, we could add in like tearing, you know, like physically crushing, all that. So tearing, crushing, but so all that's physical changes. And so now let's think about chemical changes. Again, thinking back to last week's lab. And so a chemical change is just defined as something that alters the composition of matter. And so atoms are rearranged. And most people are familiar, such as like rust. So you start off with your nice, iron nail here. And then, of course, it gets exposed to the air and begins oxidizing. And by oxidizing, we mean adding oxygen. So, of course, it changes structure as well, so you can kind of compare that. And so they combine and make a new substance. So there's iron 3 oxide. And so just a quick practice, right? Write your formula. So it's iron 3. Oxygen is -2, so do our swap trick. Fe2O3 for our formula, right, for iron oxide. And so what were some examples or signs of a chemical change that we saw last week? Yeah, I like so. I don't remember which one it was. One of the foils rusted. So foils rusted. So that's a good observation. So talking about our single displacement reaction. So if you remember, that was copper sulfate plus zinc, and that gave us back copper. And so that was that rust coloration that looked like. So that's a good example there. What else do we remember kind of seeing? What else is evidence of new substances? Oh, yeah, so our color change reaction, making our iron thiocyanate complex. Other things that we remember. So bubbling's always a good one. So bubbling always tells us that we're making some sort of new gas. Oops. And then anything else that we notice with chemical reactions?
Dissolving the magnesium.
So dissolving magnesium. So both making gas and, of course, turning it into ions. What else do we have? What did you say, burning? So burning's another good example. So this is pretty good. Any other thoughts on how we can identify kind of what's going on or clues that we have a chemical reaction? So this is a pretty good list. And so, right, I like what you guys were telling me too. So we're seeing, right, the kind of the rusted, we have color changes, right, gases, dissolving, burning. So all of this is giving us a clue as to what our product will be as well and how we can write that. And so, of course, we've gotten a small taste of this. And so, again, anytime we have our chemical change, then we have our new substance. And again, I like all these examples we gave of how to identify our new substances. And then, of course, so this is super important for a practicing chemist. So every time you do a new research reaction, you always write at the very top what you're going to be doing that day. And so you always have, right, reactants, so your starting materials, and then you always want to write your products, or at least in the case of research, what you hope you will make if it's a new reaction that you've never done before. And so our reaction is a written statement, and it seems pretty simple, but it's also, right, extremely powerful. And so we'll go through. So in this case, we have methane plus oxygen reacts to give us CO2 and water. And then does anybody remember from our lab what type of reaction this is? And try. Yeah, combustion. So let's, and I'll make a new space over here. So I'll rewrite our reaction types as well as we go kind of through some examples. But a combustion, so remember the general formula for that is some hydrocarbon, so a carbon, a hydrogen, and sometimes oxygen. So right, sometimes it doesn't have oxygen. It doesn't really matter what formula it is. And then it's always plus oxygen, and then it always gives us CO2 and water. And so this is considered a complete combustion. And so for our purposes, we would always have some sort of complete combustion with CO2 and water. And the only reason I say complete is if you have some sort of incomplete combustion, or usually this is when something's like malfunctioning at home with like a space heater or something. If you have an incomplete combustion, you also get carbon monoxide as a product. And so that's where like those dangers come in. They say like that's why you need a carbon monoxide monitor for your like space heater. Is if something's not firing correctly and then it's doing incomplete combustion, that's where you get the carbon monoxide. But again, complete combustion is only CO2 and water. So I'll just put this as a fun fact, just so you know that. And so we saw different types of combustion in our reaction as well. So let's go over the other type. So we had, this was, I'll call this more like our organic combustion. But then, if you remember from your lab, you also had this special combination combustion. And so combustion just implies some sort of, right, burning in the presence of oxygen. But then with those combination combustions, like the one with magnesium plus oxygen, it's usually some sort of metal, and then it combines with oxygen to give you your metal oxide. And so you could put like iron in this category as well, obviously on a much slower time scale. And then the combination just refers to the fact that you have two things making one product. So if we were to just define combination by itself, then it follows just the simple form of more reactants and products. So A plus B gives you one AB overall product there. All right, so questions about combustion, and combination so far? And so we go back to this. And so again, what's also powerful about this short little statement is it tells us a clue of how we're going to be doing the reaction. So in this case, they're all in the gas phase. So if you need to remind yourself, I think we talked about this previously, but again, just remind yourself, G is gas, L means a liquid state like water or maybe ethanol, something that is a liquid. Solid, or S is just solid, like if you're adding, pure like calcium carbonate powder or whatever. And then we have AQ, which means aqueous, so it's just dissolved in water basically. think I misspelled aqueous. Let me try to spell it again. There we go. And so again, that's just anything dissolved in water. And you probably have seen that in lab with our little dropper bottles, how we always have our chemicals in water. That's a little AQ solution. And so the other powerful thing about this, and again, you got like a tiny taste last week, but we also want to eventually balance our equation. So this one is not balanced, but we want to write a balanced equation so we know kind of our relative quantities as well, such as like writing, a recipe for your cake. So you know how much flour and eggs and sugar you need to have in all those ratios. And so again, it's our shorthand, so super powerful information. And so first step I always say, right, is we want to write our correct molecular and ionic formulas. So this is kind of the only thing that comes back to haunt us. And so somebody was asking, what the final is going to be on. And so the final is mainly focused, right, on the second half of material. But such as in this case, right, we still have to know how to write our formulas properly to set us up, to do the stoichiometry. And so just start that, right? It's kind of the first thing is like no matter what, just start out and write the proper molecular or ionic formulas. And right, you want to balance the charges and make it all proper. So once you do that, then you can focus on the stoichiometry and the balancing equations, but we'll talk more about that. And then again, we would write our states. So this is useful for the practicing chemist. So you kind of can mentally prepare what your reaction is going to look like, what are you going to have to do. And then we'll practice this. So you, again, did that last week where you were balancing out the number of atoms on each side with your coefficients. And so we'll do that. And again, that's super important for our recipe. And then all this can then, of course, be used to determine the weights of our reactants. And again, that's super important, right? As a practicing chemist, you need to know, well, do I even have enough material to make whatever I'm trying to make today? And then once I'm done, how much product should I have? And you want to know that answer both so you know how much to expect and tell, did you recover all your product? Is a lot still missing, or did you have a bad reaction? And so you have to at least have some idea of a yield. And so all this is dictated by our law of conservation of mass. And so again, right, we said that we're just rearranging our atoms. And so that means we have to have the same number of atoms on each side. And so again, we balance the equations by balancing atoms, so using, right, our coefficients. And so if we look at this example, and so they already balanced it for us, but we can back up for a little bit. And so we can start off, so methane plus O2. And again, right, don't forget all your diatomics. And I have extra periodic tables if people need, and I can make more. And then, so you have to start trying to balance. So we can look at our carbons. So one carbon, that's okay. Then we have 4 hydrogens and then only 2 here. And so a good guess is to put a 2. So again, we only use our coefficients now once we write all our proper formulas. And so now I have 4 hydrogens. And let me add up my oxygens. So 2 plus 2. So I have 4 on the product side. So I need 2 on the reactant side. And so that gives us what they provided as the answer up there. And so again, you probably have had a small taste of this last week. And it is a lot of, guessing and checking. and you're trying to maybe reserve the atoms that are not involved, that are by themselves kind of at the end, like oxygen here, right? We did that one last, and you want to start with like carbon and hydrogen since they're involved in compounds. And so this reaction stoichiometry, this week's lab, will hopefully help put this in perspective as well. What's it all about? And so again, right, these coefficients give us the relative amounts in moles of each of our substances. And so in this case, right, we can translate this to mean a lot of different things. So we have 2 equivalents of octane plus 25 equivalents of oxygen give us 16 equivalents of CO2 and 18 of water. And so, right, we can say that this is moles. So 2 moles reacts with 25 moles to make 16 moles of CO2 and 18 moles of water. Or we could also talk about individual molecules. So, right, 2 molecules reacts with 25 molecules to form 16 molecules and 18 molecules. And then, of course, right, we can scale up and down, appropriately, however we want. So we can half it. So we could do a 1 to 12.5, right, to 8, to 9. This can be molecules, this can be moles. You can times it by, 100 or 3, or it doesn't matter, right? So let's say you need to scale up times 3. So just like at home, you're trying to scale up a cookie recipe, so same thing. So now 6 octane plus 75O2. What's 16 times 3? 48. 48 CO2. Anybody got 18 times 3? I will take it plus 54 H2O. So these are all just ratios, right? We can scale up, we can scale down, we could do 0.2, we could do 0.1, 0.002, it doesn't matter, just as long as they're all in this ratio. All right, so let's try to do this in terms of kind of thinking about food, and then hopefully it'll translate to chemicals. And so right in this case, if we're looking at our pizza recipe, so just like you would at home, so we have, right, 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese gives us 1 pizza. And so we could express this just as a ratio as well. And then of course, if we wanted to scale up, we can figure out basically our limiting reagent. So if we have 10 cups of cheese, go back to our balanced equation, aka our recipe, and then we can set up our ratio. And so now this is just dimensional analysis. So if we have 10 cups of cheese, then we can make 5 pizzas. All right, so let's try this with some s'mores examples. And so let's first write our equation for s'mores. And so let's at least start with 2 graham crackers. So now this is my formula. And then, so how many marshmallows do you like to put in your s'mores? 1. So 1, I'll put a jumbo marshmallow in there. And so there's our jumbo marshmallow. And then I'll put 3 little squares of chocolate. So 3 chocolates. And so all that equals, right, our 1 s'more. And so now let's start off with one type of problem. And so let's see, how many people are here today? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if we want to make 20 s'mores, so how many chocolates and graham crackers do I need? So take a minute or so to do this. So do we have thoughts, answers, questions?
40 graham crackers.
So 40 graham crackers
And 60 chocolates.
and 60 chocolates. And so let's just go through how to do this. And again, it seems pretty simple right now, but you want to keep these principles from when you're doing your mole ratios and everything later. And so how do we get there? And so again, right, this is our balanced equation, so we always want to refer back to this. And so then we can write kind of our ratio. And so we have 20 s'mores, or we want to make 20 s'mores. And then, so if we want to do graham crackers, so this is our conversion factor then from our balanced equation, right? So from our equation, and again, seems easy now, but don't forget these basic principles when we look at different numbers. So we have 3 chocolates, give us 1 s'more. And so now we set up our dimensional analysis. So 1 s'more on bottom, 3 chocolates on top. And so that gives us the 60 there. And then we can repeat that for our graham crackers. And again, we started with 20 s'mores. Then we go back, get our, so this is our mole ratio essentially. So 2 to 1 now. And so now we'll set up 2 graham crackers for every 1 s'more. Excellent, giving us 40. All right, so that's one type of problem that you will see. And so next, let's try a little bit more difficult of a problem. And so this one I would call it a limiting reagent problem. And so let's see. If I have 77 chocolates, 15 marshmallows, and 32 graham crackers, How many s'mores can I make? So try this for a minute. Do we have answers or still working? And so for these limiting reagent problems, usually what you have to do is kind of go through each one and do the calculation. And so let's kind of look at that. So if you had 77 chocolates, how many s'mores could you get from this? So 25. That sounds right. And so you could set up, again, just formally the math. So you have your ratio. So 3 chocolates give us 1 s'more. So now 3 chocolates goes on bottom, 1 s'more on top. So that sounds like 25 on that one. And then, so what about 15 marshmallows? How many could we get? How many s'mores?
15.
So 15, so we said there were a 1-to-1 mole ratio, so I'll just write that out. Again, just formally as part of the work. So 1 s'more, so 15 s'mores. Excellent. And then what about 32 graham crackers? So how many s'mores could we make?
16.
So 16. So excellent. So again, I'm just writing it out from our ratios. So every 1 s'more takes 2 graham crackers. And so now looking at this one, which is our limiting reagent? So marshmallows. And so now we would identify, so limiting reagent, AKA it's going to run out first. And so we can only make 15 s'mores. All right, so now let's see if we can switch it up just a hair. And so now let's look at a chemistry problem and hope that everything you did doesn't fly out of your brain. And so let's look at this one. So this is kind of interesting. We don't normally have a combination reaction involving 3 substances, but here is one. So 2 equivalents of nitrogen gas plus 4 equivalents of water plus oxygen give us 2 equivalents of this ammonium nitrate. And so now we can say if I have 60 moles of water, ten moles of O2, and 50 moles of nitrogen. So what is my limiting reagent? So same problem. We just switched out our nice friendly graham crackers for scary looking formulas. And yes, the top equation is balanced, so you don't have to worry. We'll give people like another minute or two. And so let's start going through them, and let's go through this setup. And so just like before, we just want to look at our mole-mole ratios. And so in this case, so we start with 60 moles of H2O, and then we can look at our conversion factor. And so this one, right, don't let it trick you that we have two equivalents of product. And so again, we still just care about their mole-mole ratio. And so in this case, for every 4 moles of water, we get 2 of our product. So we set it up like that. So then how many moles of ammonium nitrate do we make from 60 moles of water? So 30. So is that what we all got? Or did we get tricked? Yeah.
The second one, what does it say after the 2?
Sorry, where?
Like, after the parentheses, what's like the top part of that?
This?
Yeah.
So this is the ammonium nitrate. So I'm just rewriting. Basically, I'm writing our conversion factor, right? So just the relationship, since we care about water and product. So I just wrote that conversion factor with water being on bottom there. So then we just need a repeat. And again, don't let all these little numbers fool you. So that's why I wrote it pretty explicitly with the s'mores. And so just set it up again. So now we have 10 moles of oxygen. Then set up, right, your conversion factor. So now it's a 1:2 ratio. So for every 1 mole of oxygen, right, we get 2 of our ammonium nitrate. So if you have 10 moles of oxygen, how many moles of product will you have? So what do we get here? So 10, but then it's 10 times. So it should be 20. And you can go back to here, right? So they're in a 1:2 ratio. So it should be 20 moles of ammonium nitrate. So this is all moles. So right now we're in moles. And so now let's try our last one. So we have 50 moles of nitrogen, and we might not have to set it up, so we could do a quick, so look, they're in a 1:1 ratio, so it should be the same, but we could formally set it up as well. So 50 moles of N2, and again, I'm just rewriting this conversion factor, but it just gives us 1. So it's a little trivial, but I'll do it anyways. So that cancels, so we get 50 moles of ammonium nitrate back out. All right, so looking at this, what's our limiting reagent here? So O2 is our limiting reagent. Okay. You're still feeling okay? Did the chemicals trick us? So we'll go back to s'mores now. So we'll kind of alternate. And so now let's think about the next type of product. So unfortunately, we don't just talk about, right, nice moles and stuff. So you physically get stuff, right? You like a pile of powder, and then you put on the balance, and usually we're always talking about grams. And so let's write what I call our molecular weights now of our substances. And so for our graham cracker, our molecular weight is 55 grams per mole. Our chocolate piece is 12 grams per mole. And then our marshmallow is 40 grams per mole. And so let's start.
First number 55.
Yeah, 55. Try to rewrite that. I don't know if that helped. And so let's just start with an easier problem. So what is the mass? Let me make it slightly thicker. And so let's just say, right, using conservation of mass, what is the molecular weight of a s'more? So let's just start with that. And if I need to scroll to show the balanced s'more formula, I can. Do we have answers? So this one we can just add everything up, right? So I have 186. Is that what other people got? The marshmallow, yeah, is 40. Oh no. So we have 55, 12, and 40. And then just working that out. So 55 times 2 plus 12 times 3 plus 40. And so let's write this 186 up here to help us with our next problem for our s'more mass. And so we could have a problem that says something like Let me make this darker. So if I want 1,000 grams of s'mores, how many, and now let's say moles of chocolate will I need? And I'll also say, so how many grams is this? So see if you can figure out how you might solve this. Do we have thoughts or how we started? So what are some thoughts or? See. So you took the chocolate divided by 186? I'm not sure about that. What else could we do?
Is it 1,000 divided by 186?
Yeah, so I would do that. And so I'm not sure where the dividing the chocolate by 186 will take you. It could take you down another direction. That might be okay, but I want to translate into like kind of moles, right? Because that's where we want to go. And so this is basically saying, and so let's just pretend it's not s'mores, and we'll probably go back and repeat this with this equation. But right, let's say we want 1,000 grams of this product, and so we have to put it back into moles, right, to go back to this equation here. And so let's remind ourselves, so we can only compare mole-mole ratios, at least for our purposes. So I don't want to go down the rabbit hole because you could technically mass balance, but I find that's more confusing for students. And if you want to talk to me like later about it, we can go over it. But it's better to just go back to your moles. And so I always call that kind of like our safe space. And so let's do that. Oops. So let's go back to what we suggested. And so this is also, again, we want to think about in terms of chemicals. And so this is saying, right, our s'more molecular weight is 186 grams per mole. And so if we set up our dimensional analysis with our s'mores here, so that gives us 1,000, sorry, let me make it thicker. So 1,000 grams, and this is of s'mores. And then if we want to find moles, right, divided by our 186, so grams is on bottom, that gives us moles on top. And so let's just do that together. So then we get that we want 5.37 s'mores. And so now that we have this, we can go back to our balanced equation. And so now, right, we'll do our mole-mole conversion factor. And so now I'll put, well, if I want 5.37 s'mores, and then we'll go back to our ratio. So every one s'more has 3 chocolates. And so now this number times 3, and so that gives us 16.12, right, moles of chocolate. And then it asks for it in grams as well. And so again, going back to this answer, or this, what it's saying, right? So it's 12 grams per mole for every chocolate piece. We need 16 moles. So now we can set up 16.2 moles of chocolate. Then multiply it by the molecular weight. And so notice, right, moles cancels because of how the unit is. So if it's grams per mole, so grams per mole, moles cancel. So times 12. And so you should get something like 193 or rounded to 194 grams of chocolate. Questions about this part so far? And so now let's repeat it with this. And so we'll use the same number just for fun. So if I want 1,000 grams then of our ammonium nitrate, and let's solve for, let's do water. How many moles of H2O do I need? And then let's also put this, so what is the gram amount? So see if you can try this. So you might have to do some addition. So remember, right, you can calculate the molecular weights of your substances here. And so while you try this out, I'm going to run and make some copies of the Mole Highway. And we'll go over it. So I'll be right back. All right, so how are we doing on this problem?
Can you scroll some, yeah.
Sorry.
See the,
So do we know how to start it, or are we still? There was also a piece of information that I gave you last time that you had to kind of calculate yourself to start off. So what was that?
Didn't I have to calculate the molecular weight
Yep, of which one?
of the NH4NO3?
Yep, so that's an excellent starting point. So if you haven't done it, go ahead and tally it now. So, right, we need the molecular weight of this. So I'll give people a few minutes. And then hopefully this mole highway kind of helps. And so we're looking at moles. Oh, I forgot I have it electronically. So we have moles, and again, I always say this is our safe space. Oops. So I throw stuff everywhere. And so in this case, we were given grams of our product. And so now it kind of tells you which way to go. So if we're trying to get back to our moles safe space, so we can compare a mole ratio, it tells us divide by molecular weight to get moles. And you can see that with the dimensional analysis. And I'll give people a few more minutes to look through that.
Can we round, or like, to find the molecular weight, should we use all of the sig figs that are there, or?
So that's always a judgment call. So I usually try to give it like 2 after the decimal at least.
Will it be like, for like nitrogen, it would be 14.007, so.
Yeah, so then you could just
14.
round to 14. Yeah. So like oxygen, it's fine if you round it to 16. Hydrogen, usually you can just round it to 1. But then like chlorine, because that's like 35.45, you probably want to give it at least a 4 or 5. But and then, does anyone have the molecular weight of ammonium nitrate? So at least get people started. Yep, 80 sounds good. So about 80. Wikipedia has exactly 80.043 grams per mole, but somewhere around 80. So if you just got 80, that's perfectly fine. And then I'll give people another minute or so to try to get their thoughts. And so how many moles of ammonium nitrate did people get? What did you say? So 12.5, so that sounds About right, just a quick guesstimation. Is that what other people got? Okay, sweet. And so that's moles of our product. And so now we're back to our mole ratio problems like before. And so again, right, go back to your balanced equation. So they're a 4-to-2 ratio, so twice as much water is needed. And so we could set that up now. So 12.5 moles of our ammonium nitrate. And again, mole ratio just from our equation. So for every 4 moles of water, we make 2 moles of product. So notice how your product cancels. And so how many moles of water does that give you? So 25 moles of water. And so this is a great step if you're here. And then just the last little bit is now what is a gram amount? And so we could go back to our mole highway. So we're here at moles. And now we want mass. So now we need to multiply by the molecular weight now of water to get our grams back out for water. Oops. Lost my space. And so then the last step, so 25 moles of H2O, multiply it by our molecular weight, so about 18 grams for 1 mole of water. So then 25 times 18 is about 450 grams of water. Is that what everybody got? So I see some nods. Questions about this one? All right, let's go back to our graham crackers for a second. And so now let's try another limiting reagent type problem.
Was, for the last one,
Oh.
you said was 18 on the top?
Yeah, 18's on the top, so it's grams per mole, and then your moles cancel. Or you can go back to your highway to kind of help remind you as well if the dimensional analysis isn't quite sticking. All right, so let's go back to our s'mores here. And so let's try, we're going to do another limiting reagent problem, except it's going to be a little more difficult because we'll just have grams of everything. So if I have 777 grams of chocolate, and 556 grams of graham crackers. And then we'll say we have excess marshmallows, so we don't have to worry about that. So how many s'mores can I make? And the chocolate, if you need a reminder, was 12 grams per mole, and the graham cracker was 55 grams per mole. I'll try to rewrite that to help. Yeah. answers, or we still need time? So do we figure out, so how much does 777 grams of chocolate, how many s'mores does that give us? So I hear 21 and a half. Is that what other people got?
I got around 65.
Uh-oh, let's see. So let's set this up together. Oh my gosh, sorry. So we have two answers. And so let's set this up. So we started with grams, and then we needed to convert to moles. So 1 mole is 12 grams.
Oh, I did 36, because I was doing it times 3.
So then the 3 factors should come in later. So then once you get to moles, then you can set up your mole ratio, so 3 to 1. And then, so this gives us moles of s'mores. So then for every, moles of chocolate. So for every 3 moles of chocolate, then we make 1 s'more. So there's your 36. Let's see, so 777 divided by 12. And then divided by 3. So did we get about 21.6 then? I think that was one contender. And so that's our moles of s'mores. And then we can repeat that for our graham crackers. And so 556 grams. And I'm just doing it all in one step here. So 55 grams is 1 mole. Then we said, right, it's 1 s'more. Needs 2 graham crackers. And so did we get 5 s'mores for that one? So excellent. So about 5 s'mores. And so now we can tell our limiting reagent was our graham cracker. Questions on this one? All right, so you probably know what's coming. Let's try it again, except now we're going to use this formula. And so let's see. And so now we get to do it with the chemicals. So if I have 127 grams of water, and then 88.1 grams of nitrogen, and we'll just say an excess oxygen, so we don't have to worry about O2. What is my limiting reagent? Then if I need to scroll back up to the balanced equation, I can. So ask your neighbors too for help. So do we have answers, or do we need more time? Or hints? So let's see. So what did you get for our water? So we started with 127 grams of H2O. And then so we converted that to moles, so just dividing by the molecular weight. And then we had to go back to our equation for our mole ratio. So it's a 4-to-2 ratio. So you could simplify it 2-to-1. I'll leave it 4-to-2 just for clarity. So 4H2O gives us 2 ammonium nitrate products. So then how many moles of ammonium nitrate do we get? Do we get this answer of 3.5 moles? So I see some nods. Okay, more nods. Good, good. So we have 3.5 moles of product given 127 grams of water. So let's repeat that for nitrogen. And again, don't forget nitrogen's a diatomic. Let me pick a fatter pen again. So 88.1 grams of N2. And so again, make sure you account for nitrogen being a diatomic, so it should be 28 for the molecular weight. And then again, I'll go back to our formula. So they're in a 1-to-1 ratio. I'll just write it 2/2, again, more for clarity's sake. So you can tell I'm pulling it from our balanced equation. And so let's see, so 88 divided by our 28. And so pretty close. So 3.14 moles of ammonium nitrate. And so just by a smidge then, this makes this, right, our limiting reagent there. And of course, right, we could then say, well, how many grams of product was this? And then multiply it by our molecular weight of ammonium nitrate, which I forgot what we said, so like times 80. So we could go right back and forth. Questions on this one? We feeling okay about these stoichiometry problems maybe? And so we'll keep doing practice, but let's look at kind of the last type of problem you'll see. And let's actually see if I have some notes for this. So blah, blah, blah. So this is all what we were doing. And so the last little part is called this theoretical yield. And so, right, just to clarify, the theoretical yield is what you calculate. So for all those problems, right, we're calculating how much ammonium, so that would be our theoretical yield. So we could go back to this one. Okay, well we said, well, if we have 127 grams of water, right, I should have 3.5 moles of ammonium nitrate. So that's what's meant by our theoretical yield. And then, of course, right, and we all know how this goes. So you're in lab, right, you spill something, or maybe like half your product accidentally flies away as you're trying to take it over to the balance. And so your actual yield, right, is what you actually have in your hand, you know, when you're done, purified, and whatnot. So I'll say in hand. And then the last bit is then we would want to calculate our percent yield, because this is a huge part of chemistry, right? Did my reaction work? With what success rate? Especially if you were an organic chemist, right, trying to do drug design, you'd want to have over 90% yields at least. And so let's see, just a sample. We'll do a really simple sample problem. But the most simplest form could be so let's just say I expected to make 74 s'mores, but I broke some, or I ate some. Broke some, and only had 68 s'mores. And so then we could ask, what is our percent yield? And so, of course, right, this one is extremely simple because we were already told our final amount. So again, this would be, right, our theoretical yield that we would calculate potentially. And so in this case, all we have to do is take our 68, so our actual, sorry, let me get a fatter pen again. So 68 then, s'mores, so what we have in hand after eating them and breaking some, and then divided by what we expected to make. And so that's just 68 divided by 74. And so in this case, right, we had about a 92% yield here. So that would be good for an organic reaction. And then if you're trying to do like metal organometallic reactions, some of those are as low as like 50%, but all depends on the literature. And so let's try that for this problem. And so you'll have to calculate your grams. And so now if we do this problem, and so now let's just say using the limiting reagent from above, what is the percent yield? If I isolated (211) grams of ammonium nitrate. So see if you can figure that out. Make sure you use the right numbers. You can scroll back up to give you the molecular weight if you need that again.
Have a good day.
You too. So what did we get? Did we get our theoretical yield? And so that should have just been 3.14 because that was our moles of ammonium nitrate multiplied by the molecular weight, so about 80 grams per mole. So what do we get for our theoretical yield? Go for it. So 254 point, what did you say, 0.4? So 0.4, so is that about what people got? Let's see, no, that's about what I got. My calculator. So it could have slight variations with rounding. And so then we have to take our actual though. So right in our hand, what's isolated slash actual over what we would calculate in a perfect world. And so let's do that. So then that's just 211 divided by our 254. And so I get like an 83% yield. And I see some nods. And so that looks good there. All right, questions on all that? So let's talk about your lab in like the 10 minutes we have left. And so just plan for Wednesday. So this is all just going through the practice. So we'll probably just do more practice on Wednesday, and then we'll finish up with our reaction types. But now let's look at our lab, or one of the questions from our lab. And so the question is something, and it's a post-lab question. And it's like using your data, your equation or something, blah, 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 find the theoretical yield. And so, of course, your numbers may vary, so I'll star that. And so if you haven't had lab, I'll catch you up to speed. So basically, we have some unknown magnesium sulfate hydrate. And so you're calculating X here. And so this is where your numbers will vary. And so hopefully you should have something around like 6 or 7 should be your X. But it doesn't really matter what you get. And so it says, right, so using your data, find your theoretical yield. Well, let's go over what this is saying. And let's just say X is 7. And so then we want to write our proper equation. And again, it's fine if you have 6 or 5 or whatever. It doesn't matter what your number is, just as long as it's your data. And so with this reaction, we're saying, well, we started with this hydrate formula, and then we heated it up so it decomposed, and then we made 1 mole of magnesium sulfate and 7 equivalents of water. And then, well, then how do we find the theoretical yield? So now we kind of have to start back from the beginning and check our data. And so now you'll plug in, so using, right, your initial mass of salt. And so again, when you go to lab, you'll fill it up with 1/3 full of salt, however much that is. I'm just going to use a dummy value of 9 grams. So again, your number will vary. But what are we trying to do? So let's think about this. So let's go back to what we just finished doing. Well, essentially, right, we have to find our molecular weight of this compound. And again, your answer could vary. So kind of, let's write that out. So step 1, so find molecular weight of our hydrate. And so we'll do that. And then that means, right, we can find moles, because now we're back at our mole highway. And so step 2 will be convert initial grams to moles, right, of this compound, of our hydrated. And then the last step is, we can also do it with the proportion, but just going with what we've learned. So once we get moles, then we can use, right, our mole-mole ratio, just like we did with our s'mores and our other problems, to find our anhydrous molar amount, and then we can find our anhydrous molecular weight to give us grams. So then I'll just write that out. And we'll do this right now before we go. So then mole-mole ratio, and then step 4, convert moles of anhydrous to grams. And so let's run through what that would look like. And so I'm going to cheat a little for the interest of time. Oh, come on. I need to look at Wikipedia to cheat. And so I'm just trying to compare the different masses. So this is what I'm looking at. So I want the heptahydrate. So notice it comes in all these hydrate forms. So you'll have to see which one you think you have. And again, let's just say we said it was a heptahydrate, and you could add it all up, right? So magnesium plus the sulfur mass plus 16 times 4 for oxygen plus however many waters. And so again, with 7 hydrogens, that gives us a mass of 246.47 grams per mole. And then the anhydrous magnesium sulfate, I'll just give that as well, is 120.366 grams per mole. So now we have everything we need. And so now let's do the math. Again, your numbers will vary. So I use 9 for my initial mass. So we start with 9 grams. And again, this is our hydrate. So then we have to go from grams to moles. So divide by this. And so now we have moles of hydrate. And then we want how much anhydrous we should get. So they're in a 1-to-1 mole ratio. So I'm just writing this explicitly. So for every 1 mole of the anhydrous, we have 1 equivalent of our hydrate. And then the last step, converting this back to grams, so times 120 grams per mole. And so writing this all out, so 9 divided by 246.47 and times 120.366. And so that gives me a theoretical yield of 4.39 in this case. And so, right, this is again our theoretical yield. And then so what the problem wants you to do is then using this information, how good was your theoretical yield in actuality in lab? So kind of based off of that, you have your anhydrous stuff left over, and then you'll take the actual over this theoretical. So that's where that will come from. And then, so this is kind of the proper way to do it. You could also, if you like proportions, I was saying you could set up a proportion. So this is the anhydrous over the hydrate. So then E is equal to our hydrated mass. So X over our hydrated mass, so this would work as well. And the only reason why this works out so nicely is because they're in a 1-to-1 mole ratio anyways. Right, so that should help you, and if you encounter issues, of course, you can ask me. All right, we've probably reached a good stopping point for today. So like I said, Wednesday we'll keep practicing this. We'll keep doing our balancing equations. So So definitely grab the homework. And then we'll have a quiz on Wednesday too over our kind of last material from before the exam.